How to time logic primer for static timing. Analysis. Abstract chips for various end applications come in two types, one as ASIC and the other as FPGA. Different parameters like cost, R&D expenses, programmability are considered before implementing logic on an ASIC or FPGA. In addition to the previously mentioned parameters, backend flow is another crucial parameter that must be considered. Before taping out a chip in ASIC flow, the design goes through several phases like floor planning, clock tree synthesis, place and route, physical verification, etc. in backend flow, while in FPGA flow the implementation tool takes care of most of the backend flow with less human interaction. Be it the ASIC flow or FPGA flow, closing timing for a design with appropriate timing constraints is crucial, else the design would violate setup or hold time constraints that will eventually lead to metastability in design. So, in this article, we will go through the basics of timing closure and learn about different parameters that affect timing with practical examples. Keywords: gated clocks, virtual clocks, generated clocks, clock skew, clock jitter, clock latency, slack, long path, setup time, hold time, false path, multi-cycle path, MCP. Concept of clock in digital design. Clock is the reference point used in digital systems for monitoring the inputs and the outputs. The time between two adjacent active edges or two adjacent inactive edges is referred as period of the clock. In an ideal clock, the rise time and fall time is 0, i.e., the transition from 0 to 1 or 1 to 0 does not take any time. But in actual design, the rise and fall time of the clock is not ideal one, and this uncertainty is measured in volts/SEC and is referred as slew rate. Types of clocks. In any digital logic there are three types of clock, viz. gated clocks, virtual clocks, and generated clocks. When performing timing analysis, constraints should be applied to all these clocks so that the tool can recognize the type of clock and can group them accordingly. These clocks will be grouped under synchronous or asynchronous group by the tool. The clocks which share same source will be grouped under synchronous, and the clocks which do not share same source will be grouped under asynchronous clock. 1. Gated clocks. Gated clocks are used along with enable signal, which controls the clock supply to the flip-flop. Clock can be turned off or on by controlling the enable signal. These types of clocks are widely used in low-power design too. Fig. 3. Circuit of a gated clock. By controlling the enable, clock supply to the flip-flop can be turned on or off. 2. Virtual clocks. Virtual clocks are used as a reference point to drive output or to monitor input 1. These clocks do not affect the functionality of the design and they don't have a physical source inside the chip. 3. Generated clocks. Today's chips consist of different blocks within the top design. For example, there can high-speed block that works on fast clock, and there can be low-speed design such as memories that work on slow clock. Typically, there will one PLL, phase-locked loop, that will serve as the master clock source in the design. Slow and fast clocks are generated using clock divider or clock multiplier logic, and these internally generated clocks are referred as generated clocks. 1. A simple clock division logic is shown in the figure 4 and waveform corresponding to that circuit is shown in figure 5. B. Clock variations. When a clock is propagated in a digital design, there are three types of uncertainty that will affect the clock, namely skew, jitter and latency. All these clock variations will affect the timing of the circuit, and while analyzing timing of circuit, it is important to keep track of all these variations. 1. Clock skew. The delta in time where same clock edge reaches two flops can be different. This difference is referred as clock skew, and this is caused because of uneven delay in clock path. Based on direction of data and clock skew can be of two types, positive clock skew and negative clock skew. 1. If data and clock are in same direction, then the skew between flops is referred as positive skew, and if data and clock are in opposite direction, skew between two flops is referred as negative clock skew. Positive skew and negative skew can affect the timing if circuit in different ways. 2. Clock jitter. Because of the variations in power supply or temperature, the clock edge might be produced early or late compared to ideal clock edge. Because of this, the clock period can erratic. This difference is referred as clock jitter. Clock jitter and clock skew can increase or decrease the time available for a net to satisfy timing without causing violation. 3. So, while doing timing analysis, these uncertainties should be provided to the tool using appropriate commands. 3. Clock latency. Clock latency is the time it takes for clock signal to propagate from its source, crystal oscillator, to the clock pin of a register. Depending on the path, clock latency can be further subdivided into source clock latency and network clock latency. 3. 2. Slack and critical path. A. Input arrival time and output required time. Before we discuss about slack, it is important to understand the concept of node, input arrival time and output required time. A pin connection between cells, or from input/output to the cells is referred as nodes. Because modern ASIC, application-specific integrated circuit, consists of millions of gates, logic cones found inside those designs can be extremely complex. Hence for timing analysis, these nodes are broken down to several levels of logic gate. In Figure 7 it can be observed that there are 4 modeling pins, 8 cell pins and 2 hierarchical pins. Coming to input arrival time, it is defined as the time interval in which the input data arrives at the input pin of the cell/block with respect to the nearest active edge of the clock. The output required time is defined as the time at which stable output is required at the output pin with respect to the nearest active clock edge. Slack is defined as the difference between output required time, RT, and input arrival time, AT, 3. For any circuit under consideration, it is important to have positive slack or worst case scenario 0. If a circuit has negative slack, then the design would fail timing constraint and circuit has to be optimized or redesigned. To calculate the slack, we must calculate the input arrival time and output required time for all nodes in the circuit. Let us consider the below circuit in Figure 8 to calculate slack. The gate delay of different gates is shown in the Figure 8 as well. Input arrival time of 1 ns, nanoseconds, is assumed and 0.2 ns wire delay is taken into consideration. To calculate it, we should determine timing at each node and as described previously, the logic is broken down into several levels with timing analysis performed from each input towards the output direction. For example, take the NOT gate in the below circuit. At input B is 1 ns. Adding the 0.2 ns wire delay, at input of NOT gate is 1.2 ns. Given that NOT gate has 20 ns of gate delay, change in output can happen only after 21.2 ns. In the same fashion, AT is calculated at each output node and finally at the output pin of the circuit. After all calculations, we get AT of 91.8 ns at the output pin of the circuit. To calculate the RT, the same principle is used in opposite direction, i.e. from output towards the input. Let's assume RT of 50.2 ns at the output pin. When back-propagated, RT at output pin of OR gate is 50 ns. This is obtained after subtracting 0.2 ns from 50.2 ns. Taking 30 ns gate delay, the RT at input pins of OR gate is 20 ns. After all calculations, the RT at each input pins are -20.4 ns, -40.6 ns and -10.4 ns. B. Long path. Critical path, also referred as long path, in a circuit is the path with worst slack for. Critical path defines the operating frequency of the design. For example, if the long path delay of a design is 40 ns, then the maximum operating frequency of that design is 1/40 ns equals 25 MHz. Hence it can be concluded that the critical path is indirectly proportional to the operating frequency of the design, i.e. the longer the critical path is, the less frequency the design will function. In Section 1, we discussed how actual clock signal is different than ideal clock. This was largely because of the rise and fall delay of components such as buffers and inverters found in the clock network. In similar fashion, all wires and nets of the data path are susceptible to uneven rise and fall delay. This delay is because of the intrinsic characteristics of transistors that make up the gates found in digital circuits. Uneven rise and fall time will affect the long path of the design. So, let us consider the circuit in Figure 9 to study how rise and fall time affects the long path of the design. The input capacitance on pin A and B of NAND gate is 3.8 ff, femtofarad, and 4.0 ff. The output capacitance per load is 7 ff. The rise delay and fall delay of NAND gate is 0.040 ns and 0.030 ns. The rise and fall delay factor are 0.009 and 0.007 respectively. The output pin has a capacitance of 15 ff. To calculate the long path of the above circuit, firstly, we must calculate the capacitance on gate output pins i.e., C, D, E, and F. The capacitance on output pin of NAND gate in this scenario is given by equation 2. Fig. 9. Example for long path calculation. Timescale used is ns. Numerator represents total rise delay and denominator represents total fall delay. Output capacitance, C, equals, number of loads * output capacitance per load, plus input capacitance of each load, 2. For example, the output capacitance on pin C is given by 2*7FF/load plus 4FF plus 3.8FF equals 21.8FF. Output capacitance of D, E, and F is calculated in the same way, and the output capacitance value of 10.88FF, 11FF and 15FF is obtained respectively. Secondly, we must calculate the net rise and fall delay on each output node of NAND gate. The below equation 3 describes the formula to calculate net rise and fall delay of the above circuit. Net rise delay equals rise delay of gate plus factor asterisk output capacitance 3. Net fall delay equals fall delay of gate plus factor asterisk output capacitance 4. For example, the net rise delay on gate output D is given by 0.040 ns plus 0.009 asterisk 10.88 FF equals 0.137 ns. The net fall delay on same output is given by 0.030 ns plus 0.007 plus 10.88 FF equals 0.106 ns. The net rise and fall delay on all gate output node is shown in Table 1. Thirdly, we must calculate the relation between rise and fall function of output to the rise and fall characteristics of the input. As observed from the truth table of NAND gate shown in Table 2 below, it can be concluded that the output Z, rising, is a maximum function of input A, falling, and input B, falling, and output Z, falling, is a maximum function of input A, rising, and input B, rising. This is shown in equation 5 and equation 6 below. The last step is to calculate the total rise and fall time of each gate output based on the output function. For example, let's calculate the rise delay on gate output F. The rise delay is maximum function of D and E falling, i.e. max function of 0.341 ns and 0.343 ns. Adding 0.343 ns and net rise delay of 0.175 ns, we get total rise delay on output F as 0.518 ns. In similar fashion, total rise and fall delay is calculated on output gate pins, and the values are shown in Table 2. It can be observed from Table 2 that the long path is 0.518 ns and the path of the long path is through gate G1, G3, and G4 as shown in Figure 9. For any technology node, the setup and hold time window and clock Q delay remains constant. Given that designers need to sign off timing for a fixed frequency, clock also stays constant. So, the only variable that can be modified in the above equations is logic delay between the flops. Solving for logic underscore delay, we have the following equation 9. It can be observed from the equation that the logic delay should not exceed a particular value, else it will cause setup time violation, and also the logic delay should not be under a particular value, else it will cause hold time violation. For false path and multi-cycle path. In some digital logic, under certain conditions timing can be ignored on certain paths. While performing timing analysis, these paths can be set as false path or multi-cycle path so that timing checks are not done on these paths. 3. Because of the way some logic is designed, data transition on certain path cannot occur under any conditions. Such paths can be ignored for timing checks by defining these paths as false path. 5. For example, in Figure 11 below, A can propagate to output if select is 0 and B can propagate to output if select is 1. Any other combinations to output are not possible because of the 3. Setup and hold time. Nets in sequential circuit must adhere to timing constraints of the flop. These timing constraints are determined by the technology node and type of the flip-flop. The time period for which the data should be stable after the active edge of the flip-flop is known as hold time, and the time period for which the data should be stable before the active edge of the clock is known as setup time. If the data changes in the stable region before the active edge of the clock, indicated as TSU in Figure 10, then the flop violates setup time constraint, and if the data changes in the stable region after the active edge of the clock, indicated as THD in Figure 10, then the flop violates hold time constraint. Flop will enter a metastable state if either setup or hold time constraint is violated. 1,3,4. Way the select line is connected to common source. Another example is that of a synchronizer that is used while doing clock domain crossing. The first flop in the synchronizer circuit may or may not enter a metastable. Input setup and hold time, is and IH, can be affected by clock period, TCLK, and different delays in the design such as clock skew, clock Q delay, TCLKQ, and logic delay between the flop. In addition to different delays, clock latency and clock jitter will shift the clock edge from the ideal position, and hence these uncertainties will also affect the setup and hold time constraint of the flop. Clock Q delay is the delay between the active edge of the clock till there is a change in output of the flop. Considering all the delays, the setup and hold time constraint is expressed in equation 7 and equation 8 below respectively. All flops in the design should adhere to these equations, else the flop enters a metastable condition. TCLK2 clock_skew and is and logic_delay and TCLKQ 7 IH logic_delay 2 clock_skew and TCLKQ 8 condition. It enters a metastable condition if the signal crossing domain toggles during the setup or hold time of the first flop. In a 2 flip-flop synchronizer, the second flop ensures that the signal is stable in receive domain even if the first flop violates timing. Though the output of first flop violates timing, the final output of 2 flip-flop synchronizer circuit is stable. So, this path can also be set as false path since design ensures no timing violation occurs. The golden rule in digital logic is that the data from the launch flop should be sampled by the receive flop in the next active clock edge. This ensures that the setup time check happens at next active clock edge while the hold time check happens at same clock edge too. But, in some cases if the data is held constant for 2 consecutive active clock edges, then the setup time check is done at second active clock edge after the data is launched. For example, in figure 12 below, if enable signal changes every 2 clock cycle then the data to the flop also toggles every 2 clock cycle. If enable is held constant, then data to flop is also held constant. Setup time check can be ignored when enable is constant because data is held constant as well. These types of paths are referred as multi-cycle paths, specifying the number of clock edges for which the data is held constant is necessary when defining multi-cycle paths to ensure proper checking of setup and hold time violation is done. In this paper, basics of static timing analysis were introduced. Concept of timing violation in digital circuit design was discussed. Calculation of slack and long path were described with examples, and paths with no timing checks were also discussed. But while designing any chip, timing requirements are not met in first try. Numerous logic optimization is done until the design meets required timing constraints. These optimization techniques, ways to solve setup and hold time violation, and quick timing fixes using Verilog for complex arithmetic logic will be discussed in the follow-up review paper.